Like everybody else, I'm here to dedicate this presentation to Shiraz, my good friend Shiraz Tayabji, and I'm a little trepidatious about this particular presentation because I heard Shiraz say in his presentation this morning that the precast pavement stuff was the most near and dear to his heart, and that's easy to understand because really, when you think about the modern age of precast concrete pavement technology, which I would say started around 2001 or so, Shiraz has been there from the beginning in this area and is one of the people that has shepherded it through along the way, has been present from the very beginning at some of the first projects and has continued to be involved, and as you just heard Peter Taylor say, is going to continue to be involved in this area going forward. So I want to thank Shiraz for all of his efforts and his innovations and his guidance and his thoughtful conversations he and I have had over the years on precast concrete pavement technology, and for his actually even involving me in some of these things along the way. Starting out kind of at the ground floor, for those that may not be real familiar with the technology, the real motivation for precast pavement technology is the fact that we have a lot of very busy, very congested facilities. And if we look on the highway side, very high levels of traffic day and night, it's very difficult to find times to work on these pavements. There need to be alternatives for repairing and addressing distresses in these pavements that don't take much time but are still durable. And the same thing is true on airfield pavements as well. I didn't show an airfield, a crowded airfield runway or taxiway here, but clearly those are also facilities that we can't really afford to shut things down for very long because they are mission critical. So there's usually a need for, like I said, repair alternatives that allow you to make the repair in a very short work window with minimal disruption to the traffic, and yet are durable, providing long potential for service life, 40 years or more. And there are different technologies out there that are available, but precast concrete pavements are one of them. And they are one that's been developed relatively recently. If we look at a kind of a brief history of precast pavements in the United States, it actually goes back about 50 years. There was some experimental use of joint repairs, both partial depth repairs and full depth repairs of panels in Michigan and Virginia. And there's actually a fair amount of work done at airfields, military bases primarily, demonstration projects and trial projects in the 70s and 80s. And you see some of those listed here. But it didn't really take off, so to speak. The technology really was not adopted. We didn't see hardly any of it into the 80s and 90s, but in the early 2000s, there were 4 projects that I would consider kind of kicked things off. And they all kind of happened at about the same time. One of them was the I-35 Frontage Road project down in Georgetown, Texas, a demonstration project that was put together by Frank McCullough at the University of Texas, a professor at the University of Texas, and a number of his grad students. It was a demonstration reconstruction project, took place over a couple of years there, and 2,300 centerline feet of 8-inch roadway, 2 lanes wide with shoulders, so it's a total of about 36 feet wide. Post-tension in 2 directions, in both directions, which resulted in some fairly long effective panel lengths. The actual panel sizes, as you can see here in the photographs, were probably around 8 to 10 feet longitudinally, and either half the length, or half the width, I should say, about 18 feet wide or 36 feet wide. They did some that were full width placements and some that were half width placements. But you can see some of the photos here, and it was a real important project. It was, again, the first major precast post-tension project, demonstrated a lot of the specific construction techniques, the use of the tongue and groove system to kind of help align things, the use of the plastic sheeting to reduce friction, to allow you to post-tension effectively and draw the slabs tight together, demonstrated the effectiveness over time of the performance effectiveness of the technique. So it was a good project, and it helped to spur things on further. Another project happened around almost exactly the same time, was referred to in Shiraz's presentation this morning, the Tappan Z Bridge Toll Plaza, just north of the New York City metro area. And this was the first major construction project that was done under live traffic. About twice the square footage or the area really of the Georgetown project that we just talked about, but over 1,000 jointed concrete panels, doweled and tied together, placed about 8 to 10 per night, overnight, when the traffic was greatly reduced. And they were all placed very, very precisely using a system that was developed by Mr. Peter Smith at the Fort Miller Company. And he was assisted by Ernie Berenberg, Professor Berenberg from the University of Illinois, on some of the conceptual development at the time. And you can see they used kind of a bottom slat system for the dowel bars, which gave you a fairly clean surface. It had grout distribution channels for injecting grout under the panels and spreading the grout to provide uniform support. But the main part of the support was actually provided by this very finely graded bedding material that was placed on a pretty accurately constructed base material as well. And what this did was to allow the slabs to be placed and pretty uniformly supported even before the grout was injected under the pavement. And this allowed you to really expand the work windows. You know, for example, if you have an 8-hour work window and you've got to, within that 8 hours, do your saw cutting, your demolition, your removal, your placement of the panels, and then place grout and allow that grout to cure and gain strength, you've effectively shortened your work window. So this project demonstrated that you could use a very accurate grading system and allow traffic over without putting grout on for a night or two anyway. Eventually, you do want to provide the best possible support, but you could expand the work window and get more production per night by using a very accurately graded system. So again, this project demonstrated the viability of this particular system, very different from the one done down in Georgetown, for reconstructing in an obviously very high volume urban sort of an area, and it did demonstrate the advantages of some of the features of this particular system. There were also at the same time a couple of projects that were done at airfields. One was done again with the Fort Miller system at the Dulles International Airport in 2002 as well. A handful of panels on 2 different taxiways were removed and replaced, open to traffic after just a few hours of construction time. And then there was another one in New York at LaGuardia Airport, very similar. This was done with a different system, and in fact, Shiraz was involved on this particular system. I think you can see him here. Oh, there he is. And it involves, again, some very large panels, a couple of different designs, some conventionally reinforced, some pre-tensioned and a little bit thinner. But again, these were the only 2 major projects for precast on airfield pavements in the United States for quite a long time. But those 4 projects together, the 2 airport projects and the 2 pavement projects, did spur a lot of interest. People saw the potential. We certainly had the need with our urban areas and high traffic areas to expand the use of this particular technology. And that led to the formation of a technology implementation group, the AASHTO TIG, as they called it, or LST, I think was another term, the lead states team on precast concrete paving slabs. And this group, building on the enthusiasm from those first 4 projects, was active for about 3 or 4 years, starting in 2005. Representatives from a number of state highway agencies and some toll authorities, New York State Toll Authority and Port Authority of New York and New Jersey, as well as folks from Federal Highway Administration, academe. Dr. Berenberg was on the panel. Dr. Butch, I believe, was on the panel from Michigan State University, and some folks from industry. All the major purveyors of precast pavement, if you like alliteration, purveyors of precast pavement were on the panel as well, and that included the guys on this call here today. Myself and Shiraz were both a part of that group as well. And the products that this group produced were very useful in spurring the additional implementation of precast pavements around the country. Probably most useful were, almost in reverse order from when I've got them listed here. Specification Clearinghouse, all the specifications from the agencies that had done work were placed online in a place where they were readily accessible for people that were thinking about doing precast paving to reference those specifications and to build off of them. The panel also developed their own set of guide specs that were based on what we thought were the best practices from the existing state specifications. There were 3 separate specifications, one for the design of the systems, one for constructing and fabricating the systems, and one for approving systems. And there was also a frequently asked question list for people that were not just getting started in the area. All this stuff is still available online. It's been a number of years, but I provided the link at the bottom of the page here where you can still find all of this information and all this material. Well, this is kind of a graph that was produced by the Fort Miller Company in 2013. So it's about 8 years out of date at this point. But what it does show is the very slow increase in the number of lane miles, cumulative lane miles of precast pavement that have been constructed until you look at this AASHTO-TIG time frame from 2005 to 2008. And when that TIG work was done and all those guide specifications were out, and there began to be a number of tech briefs and things being put out, boy, you started to see the rate of increase of construction increase very, very rapidly here. And an update in 2018 was published by the National Precast Concrete Association. And as of 2018, there were more than 113.5 lane miles, and that's just of the jointed type of precast pavement. Doesn't count the pre-stressed post-tensioned. So you can see that from 2013 to 2018, this continued on a very, very steep trend. There's about 4 times as much precast built, a 4-fold increase over 5 years. So a pretty phenomenal rate of adoption. And again, Shiraz was instrumental in that adoption. He was working with Federal Highway Administration throughout this time to help states with their implementation through the FHWA's programs. There's not a lot of time here to talk about precast in general. I'm going to talk about what I think were some of the key developments along the way that helped to spur the adoption of precast pavement technology. And I would say that in my mind, probably 3 of the most important things were the advances in slab support and slab leveling, advances in achieving desired surface geometry, and in load transfer system design. Now there's another bunch of things that we could talk about that would get honorable mention on this list, but today they're kind of unmentionable. I would talk about pre-stressing for using longer panels or reduced slab thicknesses, and some of the things that Shiraz talked about earlier for repairs of CRCP pavement that he worked on with the Illinois Tollway Authority. And Peter Smith has a different design that he had worked on developing as well, I think was being implemented in Texas. But we won't talk about those any further. Let's look at the first 3 only. And historically, there have been a few different methods of achieving slab support. And I've already mentioned the grade supported approach that the Fort Miller system uses, where you very accurately prepare the foundation. You finally grade a bedding material to place on top of it. You can put the panel directly on that, and it's reasonably well supported and can be left open to traffic for a night or for a weekend. But eventually you do come back in and you inject grout and fill up the minor irregularities in support that would exist. Another approach early on was to use urethane or cement grout injection. And in this case, the panels would be cast a little bit less thick than the surrounding slabs, and they'd be set into place. And then they'd be raised to the desired elevation by a process very similar to slab jacking that we use for concrete pavement rehabilitation. Now, one of the disadvantages of the grade supported systems is that, yes, it does expand your work window a little bit, your productivity window, but it takes a lot of work to do that. You have to place the bedding material, and you've got to grade that material and wet it and compact it, re-roll it, maybe add a little bit more and make a final grading pass, because the success really depends on getting that thing graded, within just a few millimeters of where you want it to be. And that would include not only flat slabs, but also for slabs that might be on a transition into or out of super elevation. So you could have some non-planar surfaces that you're trying to grade. So that's a time-consuming operation, potentially. And I think one of the things that has really helped to increase productivity in installation has been the development, redevelopment really, of the use of slab jacks. And I say the redevelopment because if you look at this first picture here from the LaGuardia Airport back in 2002, they had some slab jacks built into that panel as well. But it wasn't really into a production mode here until the folks at Gracie Lift developed their system, and there are some other systems that are out competing with that now as well. But you can see what they have now is an embedded jacking system, so that you have a screw that's going through a sleeve here, a threaded sleeve, which is embedded in the concrete, pushes against a base plate, and that screw will lift the pavement into place. But before you even do that, it doubles as a slab lifting system. So it's a part of the slab transportation system as well. So you've got these embedded jacks, you lift the thing into place, and then you fill the area underneath with grout or urethane to complete the system. And that's what we're seeing here. They're using a drill to adjust the elevation of the panel using the screw head there, and now it's been removed, and they're simply filling the void underneath the pavement with a cement grout in this case. So I think that's been instrumental for moving things forward, and even a lot of the Fort Miller projects now, they are building these into their system. They're still using a grade supported system, but it does help to, even if you got a very, very accurately graded system, if you can take out a couple of millimeters of elevation difference across the joints, you're going to greatly improve the smoothness of those pavements and reduce the amount of grinding that is necessary to achieve a very smooth surface. And speaking of improving the surface and the way that the joints match, it is very important to match the pavement surface geometry. Anything you put back into the pavement eventually has to match the shape of the surrounding pavement surface. And the earliest slabs, of course, were all single plane slabs. All four corners of the slab, A, B, C, and D, would all reside in the same plane. Perfectly flat slabs. Slopes of opposite sides are equal. And in reality, what we have very often is situations where the slopes of the sides should not be equal. And we need to produce slabs that are warped or deformed or twisted or whatever you'd like to use, non-planar. There's a lot of different words for the same thing here. But any 3 points determines a plane, so we can determine the degree of non-planarity or warping or whatever you want to call it by measuring the distance that the fourth corner is out of plane from the plane established by the first three. And we'll often refer to that as a delta, the vertical displacement of that fourth corner. And we do need this more often than you might think. You might think it's a fairly uncommon thing. It's obviously you need it in places like this if you're doing a curved, super elevated approach ramp, for example. This had deltas as much as 2 inches on these panels here. But even on what looks like basically straight line tangent sections of roadway. You've had a pavement that's been in place for 20 or 30 years. There's been some settlement. The pavement is creep. It suffers from creep perhaps, or maybe just even very small irregularities in the way the pavement was paved can create irregularities in the pavement surface. And in this particular photo, there was deltas of as much as 1.5 inches on straight ahead roadway. So we don't often see them, and you really need to perform a 3-dimensional survey, pick up all your corner points before you fabricate your panels so you know exactly what it is that you need to fabricate, and whether or not you need to have a warped panel or you can get by with a flat slab. In the events where we do need to have non-planar surfaces, there are a couple of different options. One is to take a flat slab and simply grind it to the profile that we want to have. We have wonderful diamond grinding machines that many of the IGGA would promote, and that many grinding contractors will tell you can do the job, and they will do the job. And the advantage, of course, is that it's relatively cheap and easy to make a lot of slabs that are all flat and all uniform size and dimension. That's pretty easily done and less costly. You don't have to make individual slabs one at a time. But the negative side of it is that if you don't have good matching at your joints, you're going to have more grinding to do. You may have to remove that inch or inch and a half or 2 inches of concrete in order to provide a smooth ride. And if you're going to remove that, that means you're probably also going to increase the thickness of the slab and make that a sacrificial amount that you're grinding, because if the design thickness is 9 and you're going to grind off 1 inch, you don't have your design thickness anymore. So you have to add that additional thickness up front and grind it off. And the other thing is, of course, if you take a flat planar panel, as we see in the lower right-hand corner here, and you put it on a non-planar support surface, you're going to have to use extra grout to fill that up. And the bedding grout is fairly expensive for that rapid early strength material. So these are reasons in favor of and against using the flat slab and grinding process. The other option is to simply fabricate. I say simply, that's maybe not the right word to use, but to fabricate non-planar panels. And on the bonus side here, we don't need to do as much time in grinding, so there's going to be less cost for grinding. We don't need to fabricate the panels with additional thickness for sacrifice. We'll probably need less bedding grout. We'll be able to open the slabs to traffic without grout if we've also matched the support system pretty well. On the negative side, though, it takes a lot more data. You're designing individual slabs and fabricating individual slabs with very special formwork and a special casting table that is going to produce that warped surface. And that's as far as I know, it's a proprietary system there. It was. I'm not sure when the patent runs out. It may be running out sometime soon, but it's been around for a little while. But at least it has been a patented process. And the other thing, of course, is that if you are doing any sort of pre-stressing, the further you are out of a flat plane, the more that can induce eccentricities to the forces due to pre-stressing. And that may be something that needs to be looked at. The third thing I believe that has been very valuable has been the load transfer system options. We mentioned the super slab system had the bottom slots, gives you a nice clean surface on top. The slot itself is a dovetail on the bottom, which kind of locks the grout into place. A very efficient system that way. Early on systems included basically a dowel bar retrofit system. The slabs are cast without having any dowel bars in them whatsoever. You'd come along with ganged saw blades, cut slots in the surface, remove the material from between the slots, and retrofit dowel bars and fill it back in. Problem with some of the top slot systems, just as we have with dowel bar retrofits, is that the quality of the backfill material becomes a performance issue in some cases. It's a potential concern, and you've got basically surface repairs that are often right in your wheel path, which is a very rigorous environment to place a repair. To address these, there have been different types of top slot systems that were developed. And again, the top slots largely were a reaction, I think, of a lot of folks to the proprietary nature of the bottom slots that Fort Miller had at the time. So there was a way to try to reduce the cost by not having to pay royalty fees and so forth, and to avoid the use of proprietary products in some states. So we had the teardrop shaped top slot like you see here, which had a narrower top slot, so you're reducing the exposure at the surface. And then we have the narrow slot tops that we see here that were developed under the Sharp 2 project, and Shiraz was instrumental in the development of these. And in these particular cases, you've got the dowels are installed in those slots before the panel is dropped into the pavement, and there is a receiving hole on the other side of the pavement, or drilled in. And once the pavement has been placed, the panel has been placed, an operator reaches down in there with his hand or with a tool into that widened slot and pushes the bar into place, and then fills the slot back in. And I think if you look real carefully, you can see Shiraz here. Oh, there he is. And just so you know, that picture was taken. I took that picture of Shiraz on the Great Wall of China. And contrary to popular opinion, he was not involved in the design and construction of that wall. He's been involved in a lot of things construction related around the world, but that was not one of them. Okay, another dowel system that found some favor, particularly in California, is another proprietary system called the Baraglide system. Kind of gave you some of the advantages of both the bottom slot system and the slot system, in that it gave you a nice clean surface like the bottom slot did, but it was fairly easily installed, kind of like you saw with the top slots for the Sharp 2 procedure, where you push the dowel all the way in on the one side of the joint, and you drop it into the panel, and you've got oversized holes on the other side. Once it's in place, you insert a flat bar and push that bar into place into the other hole, and then you pour grout back down through the slots and through the grout ports to anchor it in place. And that was is again a patented system by Rapid Roadways Solutions out in California. So those, I think, are the three things that have been probably the most beneficial along the way to help accelerate the precast pavement industry. Current state of the practice, I would sum it up by saying that there have been a couple of really good publications that have been put out here in the last 10 or 15 years that have summarized the best practices for design and fabrication and installation of precast pavement systems. One of them is the Sharp RO5 report that you see here. And again, Shiraz was involved. He was the principal investigator on this project. It is fairly well focused on precast, post-tension, pre-stressed kind of pavements. It does have some information on the jointed systems that I've spent most of my time showing here, but an excellent reference about general principles for precast concrete pavement technology, and the source is linked down here at the bottom. And the second one would be the National Precast Concrete Association's Manual for Jointed Precast Concrete Pavement. The most recent edition came out in 2018. This is one that was written primarily by Mr. Peter Smith from the Fort Miller Company, formerly with the Fort Miller Company. He's retired now. And I assisted on a couple of chapters in this as well. And this is kind of the same thing with a greater focus and emphasis really on the jointed systems. And the link for that is down here at the bottom as well. If we look ahead to the future, I think that some of the places where we're going to see more use of reusable urban pavement systems. This is one system that Fort Miller has that's made possible by the use of hollow dowel bars. But the main purpose with the reusable systems is to allow the easy access to underground utilities without tearing up the roadway. You can take the panel out, do your work underneath the pavement, put the panel back in place. And there have been a few major installations of this over the last few years. New York City, Richmond, Indiana, did a few miles here a couple of years ago. So I think that's one place. Another thing for the future, I think, is the use of rapid replaced inlays of asphalt surface pavement. And this is up in Ontario. This was a demonstration project done about 4.5 years ago on the 401 near Toronto. They had very deep rutting in the asphalt pavement. They were having to mill and fill every 3 or 4 years. And precast pavement was used as a way to overnight micro mill and install and grout and open to traffic the next morning concrete pavement that would not rut and would give good performance. So that's out there. As we start to get into some of the more modern kinds of applications, there's work being done at Iowa State University using conductive concrete layers to produce heated concrete and to eliminate problems with snow removal. And you can see an infrared image here, and you can see the actual photograph. This is up in Iowa, and like Peter Taylor said, little snow up there, except for where they've got these conductive concrete panels in place. So that's another look forward. I think one that is probably of very great importance is the possibility of using these roadways to provide power to recharge vehicles on the fly. Every vehicle, the electrical vehicles as we're now creating them and using them more, has a limited range. And if you can embed inductance loops into concrete pavement, as has been done in Korea and in Belgium. These pictures here, I think, are from Belgium. They've got a few places for their buses. You can recharge on ramps and parking areas and extend the range and usefulness of these electric vehicles. And finally, can't talk about pavement without recognizing that it's a very large surface that reflects the sun. And why not? Let's absorb that sun and turn it back into power. And there have been some experimental things done where they've actually got built bike paths in the Netherlands that have been built with embedded solar panels. And they generate enough power to power relatively modest households and things. But certainly if we upscale that technology, there may be a future there for using our roadways not only as linear landfill for waste products, but also as power generating stations as well. So that brings me to the end. I'd like to just close by saying that Shiraz has seen this through from the beginning with the precast panels, and he continues to see it through and be active and being active in the future. He's been a tremendous friend and colleague over the years, and I'd like to thank him again for all of his contributions and wish him the best here in this next phase. So I'll wrap things up. Thank you.